You have a bunch of animation clips representing one specific action, but with different style or different mood, and you want to be able to blend those styles and mood during that actions. Hi, I'm Jerome, and today we'll be looking at the verb and adverb multidimensional motion blending using radial basis functions, a paper from 1999. So what the paper says is that you will have your animations that will have actions, and they will call them verbs. So you have the idle, walking, crouching, and all that kind of stuff. And then you will have adverbs on top of them representing the style or the mood. So you could be happy, sad, or even leaning left, leaning right, turning left, turning right. So all of those will be adverbs. And you can have as many adverbs as you want. And you will need to be able to blend all those animations together by just saying, I want to have my walking verb with a leaning right, happy animations, for instance. So how they would do this, first thing I would do is that I will import all the libraries I need, and I will import my character. I will extract the skeleton. You will see later why. So basically I turn my skeleton into quaternions and positions because that's what I will be working with. Creating a little mesh that allow me to display stuff on the ground. And then this is finally all the animations I want to use in my case. So I will not have moods as happy, sad, and that kind of stuff. What I will have is walking animations, and I will have the walking with turning left, walking, turning right, and two different styles, one with small steps and one doing bigger steps. So that's the animations I would have in my case. And this is all the animations I will be using as one verb. So the verb is walking, and all of those are my adverbs. So it's all the turning lefts, all the examples for turnings, all the examples for the type of steps. So this is all the animations I want to use. Now that I have all the animations I want to use and I know what the adverbs I will be using, we can start to look at the paper to see exactly how it works. And so for them, they said that you will have a lot of different motions, and then they represent the motions basically as this one, saying that you have a motion itself is a set of degrees of freedom. So for us, it will be the rotations and translation of every bones. For them, I think that because they talk about degrees of freedom as a really low level, it's probably just the rotations as Euler angle, you know, 1 angle for the elbow, 3 angles for the wrists and shoulders and that kind of stuff. So they have the exact degrees of freedom. I would be working in quaternions, and I would stay inside of quaternions, which means now that my degrees of freedom is basically the number of bones I would have multiplied by 7, because I have W, X, Y, Z for each quaternions and X, Y, Z for each translate. So a bit heavier than what they had in their mind, but it will work just the same way for us. So the way they encode the data when they do animations, they talk about the degrees of freedom. For them, any animations is actually encoded inside of a uniform cubic B-spline. So I recommend watching the uniform cubic B-spline videos I did earlier. So you have a number of control points for the entire animation, and that's allow you to get the animation back. Now, what is really interesting in this case, what they said is basically every animations inside of your adverbs. You could see that my animations have different lengths and different timing, but they will all be encoded with the same number of control points. So for the number of control points, you decide empirically how many you want of them for all of your animations, and then you will use the same number. So I will not encode my animation as uniform cubic B-spline just yet, because I have a lot of other stuff to do before I will be able to do this. First thing first, they do a time warping of the animations to get into what they call the canonical form. And basically the idea behind this is to realize that all of animations have different timings and different lengths. And we want to re-encode them to be all of the same length. So the generic timing for them will be, instead of saying I have 30 frames or 60 frames of animations, it just timing goes between 0 and 1 as a parametric functions. My animations goes between 0 and 1, and that's it. So we will stretch and squash the timing. So we will basically do time warps as in the paper, the time warping paper. And on top of this, we want to make sure that everything inside of each animations have the same timing reference. So basically, the beginning of the animation is at time 1, the end of the animation is at time 0, sorry. The end of the animation is at time 1. And then in my case, because it's a walking animation, I can decide that I want to detect when the foot hits the ground and when it's lifts the ground. So all my animations start with the left foot going down. So I will have at time 0 the beginning of animations, and then when the left foot hits the ground is time 0.2, for instance. Then the right legs go up, that's time 0.4, and then it goes down time 0.6, and then this one goes up time 0.8, and then end of the animation is time 1. So we will compute the different timing for all of our animations this way. So what I do is this for the canonical form. I've already pre-computed all the values. So you can see my first animations, the different timing I have inside of my real animation is that at frame 0, it starts. Then at frame 7, I get my first contact, 11, 23, 27, 32. So I get all of those. And basically to do this, how they do it in the paper is all done by hand, manually. So it's a manual process. So I had this little window that's allowed me to create those information. So you could see my animation 0, the value is from 0.7. So I know that at frame 7, what I have is the contact of my right foot. At frame 11 is when I decided that's when the contact from the left foot doesn't exist anymore. Then I will be at frame 23. That's when the contact will rehappen there. 23, I get the contact. 27, I don't have the contact anymore, and so on and so on. And you do this for all of your animations. So it's a manual process. It is tricky to get right, and that's usually why the blending might be a bit off when you try to blend all those info, because contact will not be exactly the same on every animations. But it's a manual process. You have to do it for every animations, but I have done it. What I will do on top of this, because all those animations come from motion captures, and I just picked a clip inside the motion capture. It's not an animation that's done by hand, which has nice cycles. I need to make those animations loop properly, so I could be able to use those animations, because the walking animations, I want to be able to make the character walk after it. So I will make the animation loop, and to do this, basically, the only thing I do is that I take the first frame and the last frame. I take the difference between the two frames when I'm here with the offsets. And now that you know how much arrows basically you have with the last frame to be exactly the same as the first frame, you just propagate that arrow slowly through time during your animation. So if I have an animation that says I have 100 frames, I would say at frame 0 is just my frame 0. At frame 1 is frame 1 plus 1% of the error. Frame 2 is frame 2 plus 2% of the error, so on. And then at the end is frame 100 with 100% of the error on top. And so I get the exact same pose. So you do this in the local space of all your bones. And at the same time, if you just do this, basically your feet would start to slide, unfortunately. So what I do is that I also compute where the foot would be at the end of the animations after I corrected it. So I get the first frame, I know where the positions are, and at the end I modify that pose and I compute where the foot would be. And now that I know this, I basically make sure that I will only change, apply that fixing, that correction that I did on the entire animations. I will only do it when the feet are going up and going down. So it starts from where it was before doing any fixes, and during the fly, it will reach directly where it's supposed to be at the end of the corrections. So that's the local offsets, and then I get the stuff when I compute the global version of the left foot and the right foot. And I'm just using the timing because I know exactly by the timings, I know when the feet are hitting the ground, so I can just use that information from the timing I computed before. So this is why I'm doing the looping now, basically. And now I can just compute the looping animations for all my animations. And what I have is these animations. So basically, you won't see a lot of difference. But if I go on spot, you see now that I have a looping animations for all of those, and they do loop properly, and everything is fine now. Now I have my looping animations that works properly, but what I need is to have them encoded as generic time, so going between 0 and 1, instead of having the number of frames as you wanted, as I had before. And so what I will do is that I will warp my animations using the timing I did to make it, to warp it using the time warps, basically. And because I'm using data at this point, I cannot just say between 0 and 1 and not having any informations. The timing will be between 0 and 1, but then I need to have the intermediate values and decide how many intermediate values I want to have to encode my data to be able to work with. And what I would do is I would say that I'd go for 400 frames, which is a lot bigger than my original animations. My original animations were only 30 frames or maximum 60 frames. So now I have an animation that will be with a lot more data when I'm doing this, but it's because the time warp sometimes will slow down a piece of the animations, and sometimes it will accelerate a piece of the animations. And I want to make sure that when it accelerates, I actually have enough data in between. So, you know, I don't want to have only suddenly zero or 2 frames in between, because it means nothing in data when I would try to compute the cubic Bezier. So I grow my animation so I know that I have something that will have enough data. So the warping is just this. It takes every range that I have inside of my time warping functions, and it will just scale all those range properly. And it does it linearly. So the paper, it was actually doing the time warp linearly between all the values. So I do the same. I will just stretch each piece of the animations linearly the same way. And what I would do on top, so what I've do this for, see now my new animations will be 400 frames long. I have 6 values, so it means that I actually have 80 frames between each of my ranges. So I compute the quaternions, all the quaternions, all the positions. I normalize my quaternions now because I did just linear interpolations without any stuff. And what is important for me now here is because I'm not working in Euler angle or any other representations. I'm actually working in quaternion space, which means that when I would try to blend quaternions together, I need to make sure that they are exactly in the same quadrant. You know that quaternions have a double cover, meaning that the quaternion and the inverse of the quaternion represent the same 3D rotation. So if for instance, unfortunately, you try to blend together one quaternions and its inverse, the rotation in between will probably do a 360 and that kind of stuff. And I don't want this. I want to be able to just blend as if it was the closest values. And the simplest way to do it is actually to make sure that every quaternions you have inside your animation would be in the same quadrant as the bind pose of your skeleton. So it has the advantage of saying that everything stays around the bind pose of the animations, meaning that any values that you try to blend together will always stay naturally inside of what the bone is supposed to do. So even if I have a value that it's might be negative or positive, something really close, it would always do the right rotations. It would never try to do the opposite and go in the opposite directions, because I made every quaternion be closest as possible as the bind pose, let's say. So that's what I'm doing here. I'm checking that the angle between my animations and the bind pose is in the same quadrant, and if they're not, I'm just inverting those, so all the quaternions are in the bind pose quadrant. So now that I have done this, what I have is all my animations now have exactly all the same length. They are all 400 frames long. That's supposed to be just the timing between 0 and 1. And I can display those animations. And then you could see that what happens is that now everything is a lot slower, but it slows down some steps, then accelerates, just to make sure that if I pose these animations, I can pick any specific frame. Here, for instance, I'm passing, so my left foot is passing the right foot, and if I check any other animations, I will be in the same at the same time with exactly at the passing stage of any style. So, and you could see for this one actually slows down and then will really slow down at this time, and then we'll have to re-accelerate quickly because the timing of those animations is really different. So that's what the time warp was used for, to make sure that all the informations hit at the same time. And now that I have all my animations into the canonical form, so they all have the same length, they all have all the frames representing the same data, I can actually turn them into a uniform cubic Bezier. And to do this, I would just do the minimize functions to find the best uniform cubic Bezier I can find to cover the animation curves. So I'm using the minimize functions, and I try to find the minimum error. And the number of control points you choose, so the one that you decide how many control points that controls one animations, it's something you choose. And in this case, I will just pick 23 control points. So I will actually now have 23 control points for each of my curves when I do this. So this is the functions to convert. And this one actually is converting all the animations. So what I will have is the quaternion and positions for all my animations, for the 23 control points for each bones, and then for each curves inside of those, so the WXYZ and the XYZ of the positions. So that's a lot of different curves that I would be converting. It would take a bit of time. I'm coming back when it's done. So now what you have is not an animations in terms of frames, but just an animation in terms of those control points. So the only thing I have in the animations are those control points here, and that's actually enough to rebuild the curve. And you can see that the blue one is the reconstructed curves, and the little dashed one are the original data. So that's for one of the animations for the hips and the quaternions X values in this case. So that's the one I've picked to display this stuff, but it works for all of the curves I have inside of the systems. And I can show that we could actually render the animation using this. So now I'm not replaying the animation itself, I'm playing the animations that was encoded in uniform cubic B-spline. And it plays at the right speed, because on top of this, I'm not only just recomputing the animation. So you could see I get the B-spline functions that allow me to take a specific set of control points and rebuild the curves. So that's the functions you have from the other video. So I'm rebuilding all the quaternions and all the positions. And then I renormalize my quaternions, of course, because they are completely unnormalized now. I did reconstruct curves separately, so I need to renormalize my quaternions. And on top of this, I'm converting back the generic time, the delta time I want to play, because I want to move to the next real frame and in real time. But then I need to find what it means inside of the generic time to move those values. So you need to say, okay, I'm moving one frame forward. How many frames does that represent? Or how many times does it represent in the generic time? Is it 0.1, 0.2, and so on and so on? So you have to go through the timings, find what were the different timings for the different time warps, and play at the right frames. So this is what I'm doing here. I'm finding back inside the generic time, what is my values? And now that I have my generic time, I can just request that correct frames inside of my animations. And that gives me basically this and the opportunity to play back any of the animations using the cubic B-spline. And we will finally be able to actually build our verb with all of this. Now I have all my animations in the canonical form and encoded as a bunch of control points for uniform cubic B-spline, not animation data itself anymore. And I can go through the verb construction one. And to build those, you actually use, that was the purpose of this paper, is to use the radial basis functions. And for each degrees of freedom, so that's the value that you will have to compute, except that you use B because that's one of the control points of the uniform B-spline. So for each of those control points now, what you will have to do is to compute radial basis functions and a linear approximation. I will not go through the mathematics on how they compute all those informations, because I've done the other videos that represent the mathematics for it. Just watch that one and you will have heavy introductions to how they computed that specific coefficients. But basically we need to find the coefficients for the radial basis functions and the coefficients for the linear approximations for every, well, basically for every control point. So there will be for every degrees of freedom, for every animations, and for every control points of every curves. That's a lot of different coefficients we have to compute. And on top of it, they do it for every control points to be able to blend those control points together. But they do it also for the timing. You know, all of our animations have time warps. And we decided that the time warps was, in this case, always defined by 6 different values, because the beginning, the first foot on the ground, the second lift, ground, lift, and so on. So that's my 6 time values inside of a time warp. And basically, we will do the same thing. We will use that same radial basis functions, but with the timing this time. We will have for every animations, for every of those 6 values, we will have a radial basis function. And that's what this class is doing. It basically allows us to give a bunch of adverbs with examples, build all the informations we want, and then fit a specific curve through it. So we will be able to fit any of our control points animations, or we'll be able to fit the timings and that kind of stuff, and that returns the coefficients we want to use. And then we could actually interpolate using those coefficients. So that's what this class is doing. And what I would do is just this. I will now actually make real adverbs, because so far I'm talking about emotions that have different direction and examples, but I haven't encoded what for me that represents inside of the adverb space. And that's what I would do here. I would create the adverb space. And basically for me, it's 2D adverb space. The first one is how much left or right I have inside of that animations. And the second part is the the style. For the angle, I'm doing something fairly simple. I take the first frame and then I take the last frame and I check what angle I have between those, and that gives me the adverbs values. It's the angle, the amount of rotations I had at the end of the animation. And the second one is the style, and now I will encode it manually because I know which animations have which style. So basically all the 7 first animations have the small steps one, and then the other animations have the bigger steps one, the 5th one have the second style. So 2 style and the angle of rotations. And so now that I have the adverbs, I can actually create my radial basis functions. And then I will start to be able to fit to get all the coefficients I need. So what I will do is that I will fit one by one, so because it will be easier to just see exactly what I'm fitting than trying to fit a multidimensional timings and all kind of stuff that I don't want to fight against swizzling the animations, the data and that kind of stuff. So I have the timing, the linear timing coefficients and the radial timing coefficients. It's basically the 6 values I had inside of the timing. And then I get the 3 values for the linear coefficients because that's the adverbs size plus 1. And then the 12 different values because I have 12 different examples animations. And I compute the timing, I fit the timing on all of them. I do the same for every point cloud, every uniform Bezier control points of any bones of all the degrees of freedom of each bone. So basically, you know, my 23 points, every bones in the characters, the WXYZ of the quaternions, XYZ of the positions, and then again the 3 and 12 for the linear and radial. And now that I have all those coefficients, I will be able to use those coefficients to actually play my animation and blend the different values. So one thing I haven't done inside of these implementations is actually what they call the verb graph. So basically what we have is the fact that we have one action, which is the walking actions, and I have a bunch of adverbs. So the verb is walking, my adverbs is all my style and rotations. And then normally you will build a graph of verbs. You will be able to do from idle, go to walk, and then maybe crouch or sit and that kind of stuff. And all of those verbs will have adverbs and all of those. And basically you build a graph of verbs and you make transitions between the different verbs. I haven't done this part because we've done this when we've done the motion graph. It's basically the same thing, except that instead of a verb, you have a complete verb and adverbs, but then you have transitions between those verbs and you blend the results between the verbs. So nothing really fancy in the verb graph itself. What I'm more interested in is now how they evaluate the adverbs, and so this is how what you have to compute. Now to compute your animations when you have the different adverbs and you want to blend them together, the first thing is to interpolate all the timings. You know, we've decided that each animations had a time warps and they all have different time warps, and then we build the coefficients for the different time warps. So we would blend together all those different time warps to find how we should normally time warp the blended results. So now we have to compute the blended time warped, let's say. And once you've done this, you could convert it into the generic time to know where you want to pick inside of all our canonical form animations. That gives us the T. Then for every degree of freedom, for every control points, we need to blend those control points together. So all the first control points of every degrees of freedom together, all the second control points of all the degrees of freedom together, and so on and so on. So it's per frame, per control points, per degrees of freedom. And then once you've done this, we could actually evaluate the uniform cubic Bezier, because we've blended the control points of the cubic Bezier, and then we could evaluate that cubic Bezier, and we have our animation. If we had to compute all of that at every frame, that would be a lot of things to compute. Instead, what we could see is that at any time when you try to evaluate the uniform cubic B-spline, we don't need to evaluate every control point. We're just interested in the 4 control points that are useful to be able to compute our values. That's what I'm showing here. It's how we could, you know, if my values can go between 0 and 1, which is my generic time, at any point, if I need to compute the values itself, I only need to evaluate those 4 control points. I don't need to evaluate the 23 of them, just the 4 relevant control points. So that's what I will do. I will only evaluate those 4s. And so finally, this is the full functions. Let's see what it does, and then we can go back to what was computing. So I have my character. It can now blend with different angles, and you could see how it does blend between them, and it can blend between different mood. And of course, I could probably do this when it plays, and that will be better. So I can walk, I can make it rotate, I could make it rotate in the opposite directions. It blends with all the values I want. And I can change, for instance, my mood also. So the mood is just changing the type of steps, and you can change the type of steps and also the directions. So everything has been merged together inside of the big systems. Now, if you watched the video about the radial basis functions and why it was doing linear and radial basis one, it was so it could do extrapolations on top of interpolation. So for instance, I don't have any example that goes further than minus something in this angle, and I can try to force it to go further. It does some kind of extrapolations, and then we said it can do some kind of extrapolation, but it's not that fancy. You could see that extrapolation kind of does something, but it's not perfect. It has a lot of issues with the looping part of the animations, but then it's even sliding. But if I'm staying into values I have, it can just interpolate those. Same for the mood. If I can blend between the two, but my mood has nothing that's allowing him to turn that big. So I will have big issues there doing the looping. But if I stay inside of values for which I had animations, it would work a bit better. So I can go completely changing the mood completely, and it all works smoothly. So as long as I have data and I'm not trying to extrapolate too much, it kind of works. I can force the foot to be on the ground. Nothing fancy here, and that's why it pops like crazy. I'm just watching the timing from the generic time to know if I'm between a flying or stick to the ground stuff, and I don't even smooth in and out those constraints. I just enforce them and then stop them at once, and that's why it pops like crazy. But basically, because my animation knows when I'm supposed to lock my feet, I'll be able to do it. And so, how this works? Basically, again, it's all the same stuff. I'm saving a bunch of information because I need the characters to be able to move along, but you compute the times. So as I said, you interpolate the 6 values of the timing, you interpolate them. So I get the computed times, the computed time warps, that is the blended versions of all the time warps. And then when I have this, I can go and compute the generic time thanks to those blended time warped. And now that I have the timing I want to have, I can pick the correct 4 control points I need to compute. I can compute those 4 different control points using the radial basis functions, I can actually blend together all the control points that need to be blended together. And now that I have those blended control points, I can actually evaluate my B-spline at the specific time I need to with those 4 control points. So I'm only computing one time now with the 4 control points, and then I normalize my quaternion, and that's it. And everything else is just to make sure that I can keep playing animations and it's keep moving forward. That's how this is working. So that was the Lockfoot. Where are you? That was the verb and adverb paper. You could see that it's a paper from 1999, and it basically has most of all the features we already have specifically implemented in this case. But if we take a game engine, what you will have your animation graph, which says, well, walking, jogging, running, and how you transition between them. And that's the verb in this case. And then you will have, inside of all those actions, you will probably have a blend tree that's allow you to decide how you blend leaning directions or blending animations depending on the style. So basically it's the same as the adverb, except that all of this was computed at once, trying to blend higher dimension systems instead of just doing a simple blend between those. So paper from 1999, which has most of the concepts we have in game engine today, although a bit more complex in the mathematics behind it. I hope you enjoyed it, and I'll see you next time.